When you get into multivariable calculus, you start dealing with these really complex surfaces in 3D space. And trying to understand their geometry, like finding a tangent plane or a normal line, can feel pretty tough. But what if I told you there's one single tool, a vector, that acts like a geometry shortcut? Well, there is. It's called the gradient vector, and we're about to see just how powerful it is.
Look, if you have a simple function, something like z equals f of x and y, finding a tangent plane is pretty straightforward. You've probably done it a bunch of times. But what happens when things get messy? What about a sphere, where all the variables are kind of tangled together? How in the world do you find a vector that's perpendicular to that? It seems a lot harder, right? But the solution is actually surprisingly elegant. And that solution is the gradient vector. So for any surface you can write in the form fxyz equals some constant, we call that a level surface, the gradient is just a vector made up of its partial derivatives. Super simple to calculate. Now you might already know the gradient as the thing that points in the direction of steepest descent, like the fastest way up a hill. But here's the geometric property that changes everything for us. At any point on a surface, the gradient vector is always pointing perfectly perpendicular, or normal, to it. That one fact is the secret weapon we're about to use.
Okay, so knowing that, we can basically write a simple playbook for all of these geometry problems. The gradient literally just hands us the exact normal vector we need on a silver platter. From there, it's just a game of plugging it into a couple of standard formulas you already know.
First up, the tangent plane. You remember the standard equation for a plane, right? All it needs is a point on the plane, which we'll have, and then normal vector. That's our A, B, C. Well, guess what? We just found the perfect normal vector. The components of our gradient, the partial with respect to x, y, and z, are our A, B, and C. You just plug them right in. It's that direct.
And you know what? It's the exact same logic for the normal line. To define a line that's perpendicular to a surface, you need a direction vector pointing, well, perpendicular to the surface. The gradient is already doing that. So it's the perfect direction vector for our line. You use the very same A, B, and C components and just pop them into the parametric equation for a line. Same vector, different formula.
All right, theory's great, but let's make this real. Time for an example. We're going to find the equation of a tangent plane to an ellipsoid. Let's put our new playbook to work. So our surface is x squared plus 4y squared plus z squared equals 18. Step 1, we define our function f as the side with all the variables. Easy enough. Step 2, calculate the gradient. The partials give us the vector 2x, 8y, 2z. Now we need the normal at the specific point, 1, 2, 1, so we just plug those values into our gradient, and boom, we get our normal vector 2, 16, 2. That's our ABC. Step 3, just plug that vector and our point into the standard plane equation. And that's it. You've got your answer.
Okay, let's move on to our second example. This time we're finding a normal line. Now this problem looks really simple on the surface, but it's hiding the single most common mistake that students make with these: the setup. The setup is absolutely everything.
So the problem gives us z equals x squared y. Now your first instinct, your muscle memory, might be to just dive in and start taking partial derivatives. But wait, stop. Remember our rule? The gradient trick only works for surfaces written in the form f of x, y, z equals a constant. So the absolute first thing we have to do is rearrange the equation. We just move the z over to get x squared y minus z equals 0. Now it's in the correct form.
And honestly, this right here is the number one error. You absolutely have to get all your variables on one side set equal to a constant before you even think about taking a gradient. That's what defines the level surface that the gradient is normal to. If you forget this step, all your calculations after that will be for nothing.
Okay, so with that crucial setup done right, the rest is just mechanics. We take the gradient of our new function, f equals x squared y minus z. That gives us 2xy, x squared minus 1. We evaluate that at our point, -1, 2, 2, which gets us our direction vector, -4, 1, -1. Then you just plug the point and that vector into the line equation and we're done. The hard part was just that first step.
All right, for our final example, let's level up one more time. What if you're asked to find the angle between two surfaces where they intersect? Now, that sounds really complicated, right? How do you even define that? But you'll see, by combining our gradient tool with an old friend from vector calc, it becomes surprisingly straightforward.
Here's the key idea, the big insight. Defining the angle between two curvy surfaces is weird, so we make it simpler. The angle between the surfaces is just defined as the angle between their tangent planes at that point. And how do you find the angle between two planes? Well, that's just the angle between their normal vectors. And how do we find normal vectors to any surface? With the gradient. See the chain of logic? So this big, scary geometry problem just boils down to finding two vectors and the angle between them. So, first things first, we find the gradient for each surface and evaluate them at the point 1, 1, 1. This gives us our two normal vectors. Let's call them n1 and n2. Then, we just need to get the ingredients for the angle formula. We need their dot product, which is 6, and the magnitude, or length, of each vector. And here's that classic formula. I'm sure you remember this one. The cosine of the angle theta between two vectors is just their dot product divided by the product of their magnitudes. And we just calculated all three of those pieces. So we plug in our values, we do a little bit of simplifying, and we find that the cosine of the angle is 1 over the square root of 3. A really complex-sounding geometry problem solved with a simple vector formula, all thanks to the gradient.
So we've seen how the gradient is this amazing geometric key, always pointing perpendicular to a surface, unlocking normals, tangent planes, and even angles. But remember its other identity? It's the direction of steepest ascent. So it makes you wonder, if this one vector can guide us so powerfully through the abstract world of geometry, where else? In optimization problems, in physics, maybe even in machine learning, could this powerful vector be pointing the way?